This exercise is to do with the graphical construction again, this time in relation to the LC filter. We've gone through the constructions for voltage transfer function, input impedance and output impedance, using as an example a high Q filter. That is, low losses where the Q is bigger than 1, and we sketched the quadratic forms in that shape. And the exercise was to repeat the same graphical construction process, but use as an example the low Q filter, taking advantage of the fact that for low Q quadratics you can factor them into two real roots. This is a summary of the two cases of the quadratic. The high Q case where you leave it as a quadratic, the low Q case where you can factor the two roots. And the two roots are Q omega 0 and omega 0 over Q. This is the summary of the same two cases in terms of the phase, and we've gone over that before. So we're applying this now to the RLC circuit, where we derived the expressions for the input impedance and the output impedance in factored pole zero form. And what we did to establish the construction for these impedances was to break it down into the building blocks. For example, the input impedance we divided into these three factors, recognizing that the quadratic in the numerator is the same as the reciprocal of the quadratic in the voltage transfer function. And what we did in the high Q case was start with that function and then simply invert it, and then fitted it on to the previous asymptote. That was the high Q case, so now we want to do it for the low Q case. And the low Q case now gives you this construction. The quadratic is inverted from what it was in the voltage transfer function, but now instead of peaking downwards for high Q, now we have low Q, so we divide it into the two separate factors. So the quadratic in the numerator consists of the real root at Q omega 0, followed by another real root at omega 0 over Q. And of course the phase graph now changes to the other type. Now we have two separate 45 degree per decade asymptotes centered on the appropriate real corner frequencies. Now there's a third factor to add, which is the 1 over S term from the denominator. That's the one that in the previous picture was the next part of the characteristic. So that's the orange line. And I've already positioned the orange line now in the proper place. Namely, it goes through unity magnitude at the original corner frequency omega 0. So all you have to do now is do the superposition. You have to add the blue and the orange lines, both in the magnitude and in the phase. And the red line gives you that combination. And in magnitude now, you again have a series resonance, but because the Q is low, it does not dip down to a low minimum. Instead, it flattens out between the two real roots before joining the final asymptote again. And in addition, of course, the phase graphs overlap a bit. They may or may not overlap depending on the values, but it's a plain superposition of the two asymptotes you get for the two separate corner frequencies. You do exactly the same thing for the output impedance. This is broken down into three factors as well. And in the high Q case, we identified the middle factor as being the high Q reciprocal of the input impedance, which we've just solved for. So we inverted that and matched it in the proper place to the R0. Then we had the inverted zero factor that we had to account for, and we positioned that in the proper place to put the omega 0 at the same omega 0 as in the quadratic. Now in that case, since we were dealing with Q bigger than 1, the corner frequency omega 0 over Q is actually lower than the omega 0. However, in the case we're considering now, the low Q case, this time the appropriate graph shows you the low Q quadratic and the inverted zero factor, the orange line this time, it still has the corner frequency omega 0 over Q, but now because Q is small, its position is above the original omega 0. So you get a different geometry of the picture even though the construction is the same. And once again, you simply have to add the blue and the orange lines in each case, and you end up with the red line as the final asymptote representing the output impedance of the LC filter. So that completes the construction of the corresponding diagrams for the case of the low Q filter, in addition to the ones we already did for the high Q filter.